All right, ammonia, which you see here, okay, ammonia is a very good nucleophile, and it's readily going to undergo alkylation when you treat it with an alkyl halide. So here we have iodomethane or methyl iodide, either way is fine, okay, which is one of the most powerful electrophiles there is. So we have nucleophile, electrophile, and you see an SN2 reaction here occurs, and then we end up with this methyl ammonium ion, and then another molecule of ammonia comes in and does a proton transfer, and we converted our ammonia into a primary amine. But as the primary amine is formed, it can undergo further alkylation to produce a secondary amine. And you see that shown right here in this step. Okay, so now we have our primary amine, and remember, alkyl groups are electron donating, so now methylamine, this molecule is actually more nucleophilic than ammonia. So it reacts again, and we end up producing a secondary amine, and you see the secondary amine here, that would be dimethylamine. And then, as you can see here from this mechanism that's shown, the secondary amine undergoes alkylation again to produce a tertiary amine, and then it undergoes alkylation again to produce what's called a quaternary ammonium salt. Sometimes you hear these referred to as quats, okay, but a quaternary ammonium salt. Now this is all well and good if the quaternary ammonium salt is what you want to isolate. Then you would just use an excess of the alkyl halide and stir it up with ammonia, and we call this exhaustive alkylation. However, what if you wanted to just make this product, right? What if you wanted to stop after the first alkylation and make the primary amine? Then this process is not going to be efficient, because if you take 1 mole of ammonia and you treat it with 1 mole of the alkyl halide, then you're going to end up with a mixture of products. You're going to get the primary amine, you're also going to get the secondary amine, you're going to get the tertiary amine, and you're going to get the quaternary ammonium salt. And thus, for this reason, alkylation of ammonia is really only useful when the starting alkyl halide is really cheap and the desired product can be separated from all the other products, or if you're trying to make the quaternary ammonium salt. Now, if you're asking, why are you showing me this if it's not a great way to make a primary amine, we're going to take a look at exhaustive alkylation a little bit more later on when we talk about Hofmann elimination. And I know you've heard of Hofmann elimination before, but we're going to talk about we're going to get into it in even more detail in this chapter. So it's going to come back. Another substitution reaction that we can use to make an amine is what we call azide synthesis. And it says here conversion of an alkyl halide to an azide, and that's via an SN2 followed by a reduction to yield a primary amine. So let me walk you through it here. First thing you need to know is NaN3. NaN3 is sodium azide. So sodium azide, and you should be able to draw the Lewis structure of the azide ion. So if it's N3 -1, right, you've got 5 valence electrons for nitrogen. There's 3 of them, so that's 15, and then you add 1 for the negative charge. You have a total of 16 valence electrons. So you start connecting the nitrogens like this. Now the nitrogen in the center has an octet, but the 2 on the ends don't. So we fill in the octets, and you can see that we have a formal charge of +1 in the middle, and then we have a charge of -1 and -1 here. So overall, if you have -2 and +1, that gives you -1. So there's the Lewis structure of your azide. And so if you just permit me to move my azide on down here, your azide is going to be your nucleophile, right? And it's going to do your SN2, nucleophilic attack followed by loss of leaving group. And then we end up making what we call an azide, okay? So this would be like an organic azide. And then we can reduce that azide 2 ways. We can reduce it using hydrogen and platinum, okay, like you see here. So just a straightforward reduction like we've seen for alkenes and alkynes, etc. Or you can reduce it using lithium aluminum hydride and water. Now, I'm not going to bother you about the mechanism of the reduction, and it is shown, this mechanism is shown on the next slide. But the main thing I want you to realize here is that you've got 3 nitrogens in the azide, but you're losing 2 of them. So that means that you're liberating nitrogen gas somewhere along the way, And you guys know that gases come out as bubbles, so that means it's going to leave your reaction flask and is certainly not coming back into the reaction flask. And so based off of Le Chatelier's principle, this is going to help drive the reaction forward. And here's the mechanism right here. Okay, I already drew this first step on the previous slide. Okay, remember this is just our N3 here. That's your organic azide. Then you see there's a nucleophilic attack by the lithium aluminum hydride, and then it undergoes the loss of leaving group. But what's our leaving group? It's nitrogen gas. Okay, so it says nitrogen gas is expelled, and again, it's not coming back into the reaction flask. So after treatment with water, you end up forming your amine. And so, like it said on the previous slide, this is a better way to make an amine than alkylation. And the last way in this video to make an amine via substitution is doing what's called the Gabriel synthesis. And Gabriel synthesis works for the synthesis of primary or secondary amines from what's called phthalimide. Yeah, try that one on, right? Phthalimide, okay? So this is phthalimide down here. You treat that with potassium hydroxide and you make potassium phthalimide. Now, while I was drinking my coffee this morning, I said, well, I know from experience that potassium phthalimide is a commercially available compound. It can be purchased. And so I wanted to see how much it costs. And I'm sure you could Google it and probably find another supplier. But the first one that I found, it was $100. It was $100 for 500 grams. So you get half a kilogram of it for $100. It's a pretty good deal. So potassium phthalimide. And the reason this deprotonation works so effectively with potassium hydroxide is because this proton has a pKa. pKa is about 8.3, okay? And that's because you've got the electron withdrawing group here, right? And here as well. And you could draw several resonance contributors to the potassium phthalimide. I won't spend too much time on that, but anyhow, you could draw those in. So we effectively deprotonate the phthalimide, make the potassium phthalimide, and you can see that now we've got this negative charge plunked on this nitrogen. It's going to make a good nucleophile. And so we can use our potassium phthalimide as a nucleophile to do an SN2 with some kind of alkyl halide. Okay, so now you see that we have our alkyl group attached to the nitrogen. So now if you're wondering, okay, that's great, but what are we going to do with all of this? How are we going to get rid of all that piece? Well, there's actually a couple of ways we can do that. And both of those ways are shown here, okay? So one is using aqueous acid. So we just hydrolyze the whole thing with aqueous acid. So you can see you're breaking this bond here and this bond here, okay? And that releases what's called phthalic acid. So that's phthalic acid. But since you're an acid, you end up with an ammonium ion like this. So that means you would have to treat that with a base, right, to regenerate your amine. Okay, so that would give you an extra step. And I've taught this class for a long time, so I know that my students prefer this method here because it's one step, okay? And NH2, this is called hydrazine. And so you can see how the hydrazine gets incorporated into the structure of the phthalimide, okay? And then you end up liberating the amine. So I think if you look at the solutions manual, I think he almost exclusively uses hydrazine for breaking apart this phthalimide intermediate here. All right, using a Gabriel synthesis, show how you would make each of the following compounds. All right, so we know that our nitrogen is going to come from our phthalimide, right? And all the rest of the molecule, this is going to come from our alkyl halide. So if we do a retrosynthesis, we're going to need the phthalimide, the potassium phthalimide, obviously, but our alkyl halide is going to have all of these carbons in it, right? So we'll put bromine, you could put iodine, you could put chlorine, doesn't matter. Okay, so let's pencil the whole thing down and I'll show you what the expectations are. So first you want to draw the phthalimide. So it's a 6-membered ring that's aromatic fused to a 5-membered ring. You get the nitrogen there. Okay, and for some reason, if you look in the solutions manual, he always wants you to make the potassium phthalimide. So we'll just put in that first step, potassium hydroxide. So then we're going to put in our alkyl halide, right? At this point, we would have synthesized the potassium phthalimide. Maybe we don't have $100, to spend on it. So You know, times are hard. Okay, so anyhow, so then we put in our hydrazine at the end, and that's going to give us our product, just like that. Okay, for the next one, the nitrogen, again, that's going to come from our potassium phthalimide, and all of this, right, all of this portion here is going to come from our alkyl halide, and so our alkyl halide, I'll just use pH instead of drawing the whole aromatic ring, is going to look like this. And you could have chosen iodide or chloride. I chose bromide. Either one is fine. And so what's our synthesis going to look like? We're going to start with our phthalimide. And I'm going to give a little more detail on this one. Why not? So in the first step, again, when you treat that with the potassium hydroxide, it makes the potassium phthalimide, which I told you was commercially available. But anyhow, we'll just draw the whole thing out here. So negative, and there's our spectator ion. So now we're going to treat that with our alkyl halide, which you can see is secondary. And I think secondary alkyl halides work okay with the Gabriel synthesis, but I don't think they work, or it doesn't work with tertiary. So that's the first step, and then the second step is going to be our hydrazine, and that's going to give us our product, if I can pencil it in here without being too messy. And there you have it, Gabriel chemistry, or Gabriel synthesis, the old reaction, but oldie but a goodie, still being used to this day. You know, Gabriel synthesis, I'm not sure what year it was discovered. I know it's a while ago, but it's one of those things where, you know, it's just so good. You know, it was so robust, works so well that people are still using it today to try and design modern medicines.